Good evening. Welcome to Open House Edition 18 by DDAG. I am Mugdha, your host for the evening. Today we have with us Mr. Anil Kumar Mehrotra, consultant and faculty geostatistics with DDAG. Today he'll be talking about geostatistics and its application in mineral exploration and geotechnical engineering projects. Mr. Anil Kumar Mehrotra has done post-graduation in geology from Lucknow University. He served Mineral Exploration Corporation Limited for nearly 40 years in various capacities and superannuated as Deputy General Manager Exploration in 2014. He has vast experience in exploration of various mineral deposits such as coal, lignite, copper, lead, zinc, and gold located throughout the country. He worked extensively on computerized processing of exploration data and creating 3D ore body modeling of various non-coal deposits. He has more than 20 exploration reports to his credit and has presented many technical papers in national and international seminars. He also has wide experience of imparting computer training to officials from several government organizations. He has received professional training from Center of Geostatistics Fontainebleau, France, and was awarded postgraduate diploma in advanced mining geostatistics from Ministry of Industries, France. He was project in charge from MECL side for a collaborative project entitled Estimation of Syncrude Potential of Oil Shale in Northeastern part of India in Assam and Arunachal Pradesh with BRGM France, MECL and Directorate General of Hydrocarbons. After superannuation, he is a guest faculty in Geology Department of Lucknow University for teaching economic geology and geostatistics to undergraduate and postgraduate students. With this brief introduction, I now request Mr. Anil Mehrotra to take the stage and start with his presentation. Thank you.
Okay, thank you, Mugdha, for introducing me. Can I start now?
Yes, sir, please go ahead.
So, at the outset, I am very much thankful to the Academy for giving me this opportunity to share my ideas with this August gathering. I am highly indebted to Dr. Gopal Dhawan, founder and chairman of the Academy, for providing me continuous support and guidance during this endeavor. I am very happy that I have worked with him in MECL also for more than 3 years. Now I am again working with him in this academy. So I'll be talking on the topic of today is geostatistics and its application in mineral exploration and geotechnical engineering projects. Regarding my introduction, Mugdha has already told that I was superannuated as Deputy General Manager Exploration from MECL. Then presently I am Honorary Faculty Department of Geology, Lucknow University for underground and postgraduate students, undergraduate and postgraduate. Then guest faculty in the DDAG. Then senior consultant in mineral exploration and resource estimation, utilizing geostatistical techniques in AWR Llyod, India Private Limited. I am a life member of Mining Engineers Association of India, MEAI. My email ID is given. My website is this. I have my YouTube channel with the name Anil Kumar Mehrotra. The link for my YouTube channel is provided on upper left-hand corner of my website. 3 links are provided: LinkedIn, Facebook, and YouTube. I am author of a book also entitled Geostatistics for Beginners. The book is mainly meant for younger generation professionals who are engaged in mineral exploration, mining, and students who are interested in learning the subject of geostatistics. This book is available at Amazon, MRP rupees 599 in India, and $40 plus courier charges in actual for international market. Now I'll be talking something about geostatistics first, then go to the applications. So geostatistics, the study of variability of regionalized variables is called geostatistics. In early 50s, Professor D.G. Crick, a mining engineer working in a gold mine in South Africa, noticed discrepancies between the estimated grades of blocks and true grade obtained after mining. Professor Georges Mehrotra of Center of Geostatistics, Fontainebleau, France, thought that the underlying problem was the correlation existing between the sample values considered for estimation. This correlation had to be quantified as a mathematical function of the distance between the samples. He came out with an idea of a spatial correlation between the sample values and termed it as theory of regionalized variables and defined such variables as regionalized variables. The root cause of the wrong estimation was that the distance between the samples was not being considered for estimation. Geostatistics is an estimation technique. Now I come to the difference. People are not very clear what is the difference between conventional statistics and geostatistics. The difference between conventional statistics and geostatistics is that in conventional statistics, one deals with random samples irrespective of their location in space, while in geostatistics, location of samples in space is considered to study the spatial variability of the variable. And try to capitalize on this knowledge, an estimator called kriging, named after Professor Krigg, was developed for estimation of ore reserves and grade. Kriging is also termed as BLUE, B-L-U-E, best linear unbiased estimator. By this method, estimation error can be quantified, thus giving the prediction accuracy, which is so very important for taking an investment decision before opening a mine after exploration. Now, I'll come to the three basic questions regarding geostatistics. When to apply geostatistics, what is expected from geostatistics, and how to apply geostatistics. When to apply. Geostatistics is an interdependent scientific discipline rather than a standalone technique. Why I am calling it as interdependent? Because there are many scientific disciplines join hands together to come to a conclusion of estimation. Geology is there, geostatistics is there, geophysics is there. So there are many scientific disciplines. It has become a tool available to geologists and mining engineers for the purpose of characterizing a mineral deposit. A geostatistical study properly carried is generally expensive and time consuming, not cheap because of use of computer. Regarding this, I'll come to on this point later. What is expected from geostatistics? First point is what kind of reserves are to be estimated, that is in situ geological reserves or recoverable mining reserves. What is the end use of estimated reserves, ore reserve reporting, feasibility study, production planning and scheduling. What are relevant geological characteristics of the deposit? Geological characteristics may vary from deposit to deposit, whether homogeneous, bedded type, vein type, or disseminated type. Strike, dip, folds, faults, foliations, and joint planes, etc. These are relevant geological characteristics of the deposit. Data considered should be clearly spelled out. Primary assay data on trace cutoff. Here I'll emphasize on the initial data should be considered as primary assay data on trace cutoff. No economic cutoff should be applied. Composite zone-wise data along with associated thickness should be clearly spelled out. What are geologists' views on continuation of mineralization? Geologists' interpretation on the basis of exploration data with the help of geological cross-sections along the strike and along the dip, LV section and level or size plans at different levels on continuation of mineralization along the strike and dip. His interpretation on the basis of these data. In case of mineable reserves, now we come to the mineable reserve. What type of mining is envisaged? Open cast or underground? Economic cutoff grade to be considered here, because economic viability depends on the cutoff grade. With the change in cutoff grade, shape of the ore body changes, and on the shape of the ore body, type of mining envisaged, type of mining equipments to be used will depend. Make sure that there is a proper coordination amongst the entire team of project geologists, mining engineer, and the geostatistician. And according to me, a geologist with qualification of geostatistics is more preferable. How to apply geostatistics? Steps involved in a geostatistical study: collect and check data. Error-free data should be ensured before starting the study. Discuss with project geologists to find out type of sampling procedure followed. Change in sampling procedure during the exploration campaign and why. Because sometimes it happens an exploration campaign runs for 3 to 4 years, and in between the project geologist is transferred to some other place. Some other geologist joins and he follows some other sampling procedure. If it is done like that, then it should be very clearly explained why it was changed. Different geological zones, preferential sampling of rich zones, if yes, why? Now here I again emphasize on no preferential sampling of rich zones should be done in any case. Define regions and variables to be studied. What is volume support of the variable? Now this is a very important point in geostatistics, the volume variance relationship. I'll come to this in the next slide. Whether the data is borehole data having point support. Borehole data is having a point support. Then once we have channel sample data, pit sample data, or exploratory mining data. All these different types of data have different volume support. All different types of sample data have different volume support. Volume represented by each sample. Volume support means volume represented by each sample. Very important is samples of different volume support should never be combined. I repeat, it should never be combined. They should be treated separately. As volume support increases, because once volume support increases, variance decreases. That is, they are inversely proportional. A step-by-step description of the procedure should be given with all supporting documents. It should be understandable by mining professionals who are not well versed with geostatistical theory and jargon. Define regions and variables to be studied. Define the area and what are the variables. Suppose for iron ore, you will like to study Fe2O3, Fe or Al2O3 and SiO2 and all that. So these are the variables to be studied. What is the support of the variable? Are variables stationary? This stationarity thing I'll come slightly later. In geostatistics, I give this quotation everywhere. In geostatistics, big is not necessarily beautiful. That means preparing a 1,000-page report has no meaning if you prepare a 100-page report with concise and to the point data. Basic statistical tests: mean, variance, standard deviation, scatter plot, frequency distribution, histograms. All this is combined together is called structural analysis to be carried out. Check for outliers and their locations. And check for non-homogeneous data. Outliers may play a very important role in economics of a deposit, because if a very high value sample is there in the center of a deposit. So if you consider that sample, say 100 grams per ton in a gold deposit with average grade of 1 gram or 2 grams per ton, then the deposit becomes economically viable. And if you exclude that, then the deposit becomes uneconomical. So what to do in that case? Calculation of experimental variograms, fitting of variogram model, and use of variogram parameters. That is, there are three parameters of variogram, that is SIL, range, and nugget effect, for further interpolation of the variable. I'll come to these three parameters slightly later. Now we come to the definition of a variogram. How the variogram is calculated. Variogram is a study of average value of zx plus h minus zx square. That means value at x point and value at x plus h point. You subtract that and square it. That is the average value of the difference as a function of distance h. Grade and thickness of a mineral deposit are regionalized variables. They have a special correlation. Variogram is defined as a study of the average squared value as a function of separation h. Zx minus m. Now we come to the variance. What is variance? Variance is the difference with the mean. That is the sample value. What is the difference with the mean? It can be positive, it can be negative also, but once you square it, it is always positive. So zx plus h minus m and zx plus h minus m, x plus xh and x plus h, where m is the overall mean of zx, a regionalized variable. Zx is the realization at x, and zx plus h is the realization at x plus h. Their estimation depends on the distance between them. This interdependence is expressed in the form of a mathematical function called variogram. The variogram, which measures the average square difference between sample values a given distance h apart, the graph of gamma h, the variance plotted against h, represents the following features. It starts at 0 for h is equal to 0, zx plus h is equal to zx. If you put h is equal to 0, zx plus h becomes zx. It generally increases with h. It rises up to a certain level called SIL, C, then flattens out. Alternatively, it would just go on rising. The rate of increase of the variogram gamma h with h distance indicates how quickly the influence of a sample drops off with distance. After the variogram has reached its limiting value, C, SIL, there is no longer any correlation between samples. This is a very important distance. After this distance, you cannot predict anything after this distance with this variogram. No prediction can be done after this distance. This critical distance is called the range or zone of influence of the variogram. Different types of variogram models: spherical model, exponential model, Gaussian model, and power function model. I'll just try to give some idea about these four different types of variogram model. Sample data from ore body can often be approximated by a spherical variogram model. Converse function, variance का converse function जो है वो covariance होता है. This converse function measures the similarity of sample values and is utilized in the Kriging estimation method. Now, another terminology comes here is anisotropies. Now, I come to the anisotropies. The anisotropies are depicted on computing the variograms in different directions. If the range of influence along two directions, along dip and strike, in the horizontal plane differ widely, the ratio of the two ranges is called the anisotropy factor. This type of anisotropy That is, the ratio of the two ranges is called the anisotropy factor. This type of anisotropy is defined as geometrical anisotropy. Other type of anisotropy is encountered. For instance, if layering of the mineralization exists, then the global variation in any direction can be thought of the sum of two independent sources, one isotropic component plus a zonal component. Why I am talking of isotropic component here? If you multiply with the anisotropy ratio, then an ellipse converts into a sphere. So then it becomes isotropic component. Isotropic component plus a zonal component, which depends on the number of layers crossed. The difference between the grades of 2 points depends not only on their relative distance, but also on their difference of elevation in the layered system. This type of anisotropy is called zonal anisotropy. So higher sill is observed in vertical direction as compared to sill in horizontal direction in case of zonal anisotropy. Now I come to the variogram models. How it is represented mathematically. The spherical variogram is represented by this function gamma h is equal to c 3 by 2 h by a minus half h cube by a cube when h is less than or equal to a, and if it is equal to c if h is greater than or equal to a. This is what I was telling. After the distance of range of the variogram, there is no correlation. Where tangent at the origin meets the sill is 2 by 3a in spherical variogram. So for practical purposes, for deciding of the block size or for block model, this range 2 by 3a is considered to be on safer side for better estimation, not exactly a. So two-third of a is considered for deciding the block size in the block model for estimation when you are doing estimation of a block model. Exponential variogram, gamma h is equal to c 1 minus exponential minus h upon a, where 95% of the maximum value of the sill value is the range that is equal to 3a. It never reaches 100% of the maximum value. It reaches maximum of 95%. Or in this case also, where the tangent at the origin meets the sill at a, that is one-third of range, that is 3a. The tangent at the origin will meet the sill at distance a, is the practical range of the variogram. So this practical range is considered in the case of exponential variogram. The slope at the origin is helpful in determining the range for both these variogram models. Gaussian model can be represented by this c minus 1 minus exponential h square by a square. Range is root 3a or 1.73a. Power function gamma h is equal to h alpha with 0 is less than or equal to alpha less than or equal to 2. This is the range. It has no upper bound, thus corresponding covariance function does not exist in this case. So for this type of variogram cannot be considered for kriging because covariance function does not exist. Thus, it is seen that the variogram takes into account. Now, I am coming to a very important issue. Okay, variogram takes into account all the geological features, and it can be expected that an estimation procedure based on it can be geologically reliable. Now I come to the volume variance relationship. An important consequence of the volume variance relationship in geostatistics is that samples considered in a population of boreholes must be of the same length. In other words, same volume. Now, I'll just explain how the volume changes the variance. If you consider a deposit with only one sample of 2% and the mean grade is also 2%. So what will be the variance if you have only one sample? The variance is the sample value minus mean. So 2 minus 2 is 0. So variance for a deposit where only one sample is available, entire deposit you have only one sample. So your volume is very high, but volume support is very high. That is variance is 0. Now, if you divide this deposit into different blocks, so which have mean of 1%, 2%, 3%, and 2%. So, but overall mean remains the 2% only. But once you calculate the variance, 1 minus 2, 2 minus 2 square, 3 minus 2 square, 2 minus 2 square. So variance of this 4 blocks will become 0.5. From 0, it has come to 0.5. Now, if you further subdivide these 4 blocks into 16 different samples, four sample in one block, then what happens? Overall mean remains 2% only, but the variance of first this thing is 1, second one is 2, third one is 2.5, and fourth one is 1.5. So now if you calculate the variance of all this, it becomes 1.75. Average variance of the blocks of V, it is 1.75. Now, considering all the 16 samples within the deposit, variance becomes 2.25. So, that means from 0 to 0.5 to 1.75 to 2.25. So, hence, variance are additive. 1.75 plus 0.5 equal to 2.25. Histogram and variance are the functions of the volume support of the variable. Skewness of histogram is inversely proportional to the volume support, and so is the variance or standard deviation. The smaller the volume support, higher is the variance or standard deviation. Now I come to application of geostatistics in mineral exploration, a case study of geostatistical evaluation of a mineral deposit. Now this table shows the initial samples 2632 of P2O5. It is a phosphate deposit. This exercise was done by me only. So once you bring them to 1 meter equal length, all the samples, the number of sample increases to 3143 because some of the samples must be of a greater length of more than 1 meter, 1.5 meter or 2 meter. So once you composite it to 1 meter of equal length of all the sample, the number becomes 3143. Now, since this deposit was to be mined by open cast with a 6 meter bench height, so I tried to composite it at 6 meter length. And why 1 meter? 1 meter at the bottom to be considered. Uh, so in that case, number of samples become 565. And in case you consider 2 meters at the bottom, the samples become 535. Now you see the variance, how with the number of samples, initially it was 51.56. Once you composite it to 1 meter, 43.87, then 6 meter with 1 meter, 35.03. Then with 6 meters, with 2 meters, it is 34.73. Main idea in geostatistics is to consider the minimum variance. That is, a variance should be minimum. So for this case, this particular type of sample, 6 meter with 2 meter bottom, is considered with the variance of 34.73. Now, the basic statistical test to be carried out. So now if you see the histogram of composite samples after regularization, you can see the count of data is 535, minimum, maximum is given, mean is given, median is given, and variance is also given. So everything is given here. So this gives you an idea of entire deposit, how it is behaving. Now, the next step is the drawing of experimental variograms. I am not covering how the variograms are computed manually, but if you feed the data into a computer, it will immediately give you, within a second, it will give you the variogram. But I wanted to cover how it is computed manually, but time doesn't allow me to do this. So condition of second order stationarity to be fulfilled, that is mean and variance of the variable should be constant up to a certain distance. Why I am taking second order stationarity? First order of stationarity is mean and second order is variance. So they should be constant up to certain distance. Once they are constant, then it is called second order stationarity. Check for outliers and their locations. Location of outliers within the deposit is very important because it may affect the economic viability of a deposit. Calculation of experimental variograms. These are experimental variograms calculated in 4 different directions. Now, you can very easily see with the variogram and the variation in the range that which is the strike direction and which is the dip direction. Because along the strike direction, variability will be minimum, and in the dip direction, it will be maximum. So range, the maximum range which gives the strike direction, and the minimum range that gives is the dip direction in horizontal plane, and this one is in the vertical direction. Now the fitting, most important point is fitting a variogram model in 3 dimensions. So that those experimental variogram has been fitted in 3 dimensions here. The strike direction, dip direction, the strike direction and dip direction and vertical direction. So this is the range in dip direction. This is the range. This distance is the range in strike direction, and this is the range in vertical direction. And regarding sill, you can see in this fitted model, this is not starting from 0. This is starting somewhere above in the y-axis. So this distance on y-axis from where it starts is the nugget effect. That is C0. So nugget effect C0, sill C plus C0, and range for interpolation of variable using triggering. Now, why I was telling that this is not cheap and time consuming? Because you have to try the same triggering method with different permutation combinations to see which method gives you the minimum estimation variance. Here I have done for the 7 different combinations. That is your neighborhood means samples to be considered for estimation in XYZ directions. 3 blocks by 3 blocks by 3 blocks in XYZ, 5 by 3 by 3, 5 by 5 by 7, 7 by 5 by 5, 7 by 5 by 7, 9 by 5 by 7, 11 by 5 by 7. So you can see in this what I have highlighted is 5 by 5 by 7, which gives you the minimum estimation variance of 2.94. That means this method will be most reliable among all these things. Now, once you create a block model and you trig it, so you can slice it at every 6 meters in this particular case because of 6 meter bench height. Now, if you see this photograph or this graphics, so section-wise creaked grade and creaked variance is depicted. It can be seen that both are inversely proportional. This is the creaked grade. So here the black portion is the higher grade and the gray portion is the lower grade. And once you see the creaked variance, it is just opposite. Where that was higher grade, it is a low variance. So that means your estimation of high grade is more reliable in this area. So that means your uh, this prediction of high grade is supported by low variance. So misuse of this technique can lead to disappointment if not damaging results. Now I come to the today's topic, application of geostatistics in geotechnical engineering projects. At ground investigation stage, rock mass quality is modeled by using rock mass rating, rock quality designation RQD, fracture frequency FF, uniaxial compressive strength UCS, joint conditions JC, underground water conditions WC. Geotechnical engineering by its nature demands tools for coping with large uncertainties and variations in material properties to identify conditions prevailing in rock mass and soil, and if satisfied, could convert geostatistics into a real design aid for geotechnical engineers. Geostatistics deals with regionalized variables, the variables which have special correlation. Rock mass characteristics are also especially correlated and hence regionalized variables. They have some relationship between location and data. Major task in geotechnical projects is to model rock mass quality by using rock mass rating, which is a major parameter widely used in geotechnical engineering. RMR consists of a weighted sum of ratings assigned to RQD, fracture frequency, uniaxial compressive strength, joint conditions, and underground water conditions. So now I come to the application of geostatistics in geotechnical engineering projects. This technique can only be applied under certain conditions. There should be special correlation, that is, there should be regionalized variables that they are between sample values and they are regionalized variables. All the samples should have same volume support because of volume variance relationship is very important. Condition of second order stationarity should be satisfied. Mean and variance should be constant for certain distance. Application of geostatistics for estimating RMR parameters in geotechnical engineering projects. Geostatistics was originated to solve problems of estimation using kriging, also known as best linear unbiased estimator. It imposes minimization of estimation variance or estimation error. Geostatistics mainly uses various kriging methods for estimation of regionalized variables on the basis of structural analysis to evaluate and solve practical problems of estimation. It has also many other important tools such as conditional simulation and indicator kriging. Correlation coefficient, standard deviation, that is square root of variance, and mean are used to describe the degree of correlation between variables. The main job for utilizing geostatistical technique is to model RMR, rock mass rating, for any geotechnical project. Block triggering is used. Now I come to variable wise. Block triggering is used to estimate average values of an indicator of rock hardness and to characterize the distribution of fracture joints to understand the spatial distribution at different scales. Ordinary kriging is a different type of kriging, is utilized to estimate RQD distribution, associating the estimation of a standard error as a measure of reliability. Since RMR is not an additive variable, hence correct approach to spatial prediction is to estimate or simulate each of the parameters of RMR, RQD, FF, UCS, JC, and WC separately, which are regionalized variables, to assign a rating to the estimated or simulated value of each parameter. To obtain the final rating of RMR, sum of all the ratings is obtained. When the variable has a log normal distribution, logarithmic kriging method can be used. Random kriging can be used when the data is less, distribution is not large, and prediction accuracy is not required to be high. Factor kriging and indicator kriging can also be utilized for estimation. Now, Dr. Sanjay Rana, chairman of AF Academy, provided following additional information regarding use of geophysics along with geostatistics for the areas where prediction accuracy obtained by geostatistical techniques is not up to the mark. In order to complement geostatistical techniques, the areas where estimation variance is found to be higher, help of geophysical techniques can be taken as follows. Seismic velocity measurements can be used to estimate RMR parameters based on data of limestone, mudstone, marls, and shales at a dam site at Wadi Mujib, Jordan, at Jordan, El Naka 1996, obtained an empirical correlation between RMR and P wave velocity. RMR is equal to 59.8 VPF divided by VPO to the power R of 0.26. R is equal to 0.84, where VPF is the P wave velocity of the in situ rock mass. VPO is the P wave velocity of the corresponding intact rock, and R is the correlation coefficient. Shah et al. 2006 obtained a simple linear relation between RMR and shear wave velocity measured using a refraction microtremor technique in order to evaluate the rock condition for the design of a proposed railway tunnel at a site consisting of different types of granite and felsite, and volcanic rocks, dacitic tuff, and andesite. RMR is equal to 36.2 into Vs minus 10, where Vs is the shear wave velocity of the rock mass in kilometers per second. Banks 2005 derived an empirical relation between basic RMR and the slope angles in mature natural rock outcrops. Basic RMR is equal to 0.4s plus 52, where basic RMR is the RMR without the adjustment to account for the influence that discontinuity orientations may have on a particular application. And S is the slope angle in mature natural outcrops in degrees. The prime reasons, now I come to why it has not been utilized till date. Prime reasons for geostatistics not being utilized as a tool for design of a geotechnical project include widespread unfamiliarity with the concept of geostatistics, lack of a dedicated geostatistical software that can be really used in estimation of geotechnical parameters constituting rock mass rating. Now I come to a success story of application of geostatistics in finalizing the alignment of English Channel Tunnel project by BRGM France. That was way back, almost 30 years back. This is the photograph of the channel, English Channel Tunnel project. This is the channel, and this has to be bored between these two lithologies. That is the chalk marl and gold clay. This is the chalk marl, and this is gold clay. Gold clay they had to avoid. So estimation by geostatistics was utilized for demarcating the boundary of gold clay and chalk marl. And you can see this is the UK sector This is the England sector and this is the French sector. And both of them started from their side and they come here and join at the same point. This is the accuracy of estimation. So this exercise was done by BRGM France. This is a milestone success story of application of geostatistics in design of English Channel Tunnel project. It enabled careful assessment of geological risk and was used to optimize the alignment of the tunnel. While selecting an optimal alignment for the tunnel, a governing criteria was to ensure that tunnel was bored only within the chalk mark, avoiding the gold clay lithology. Triggering a geostatistical technique was used to determine the boundary between chalk mark and gold clay based on available data prior to the construction. Contours of standard deviation of predicted depths of this boundary were also generated. Geostatistical analysis enabled engineers to improve the tunnel alignment. The standard deviation contours helped to identify the tunnel sections at which improved precision was required, which in turn enabled design of successful complementary geophysical surveys of the seafloor. As the data became available from these surveys and ongoing construction, tunnel engineers used geostatistics to repeatedly improve the spatial model of chalk mark and gold clay interface. The result was that the channel engineers were able to keep the risk of penetrating the gold clay at acceptable levels and were able to achieve their objectives of avoiding the gold clay formation. Conclusions. Geotechnical behavior may significantly impact in the cost and performance of projects in hydropower projects and tunnels. Prediction of critical geotechnical parameters is one of the most relevant requirements for such projects. It should be utilized not just during the ground investigation stage, also in data processing and interpretation stage. Thus, geostatistical techniques provide an interesting alternative to traditional approaches. It gives a more precise estimation with minimum estimation variance by taking into account and using special correlation between sample values of the variables. Besides, estimation technology provides prediction accuracy. This can be used for risk analysis and for the design of the project site. My opinion is that geotechnical engineers and engineering geologists should be encouraged to explore geostatistical technique as a possible alternative to the techniques that are in use today. It should be tried in a phased manner on an experimental basis to make a beginning. It will give a quantum leap in developing confidence of designing of a project. Now, before I sign off, I'll request entire galaxy of experts sitting here to give a serious thought to the option suggested by me and discuss it threadbare. Thank you very much for patient hearing.
Thank you so much, sir. I now request Mr. H.L. Arora for his comments.
Thank you, Mehrotra ji. Very good explanation of geostatistics given by him. It is a very new topic for me because I was not involved in this thing. But the way he has explained the things, how we can improve upon the geotechnical aspects, and we have to give a serious thought of these suggestions that we should be as an additional tool for anticipating and estimating the geotechnical parameters. We should use the geostatistics. He has told that we should use as an alternative. I'm not saying as an alternative in the start, but we should say as an additional, so that we can compare the results between the two, between the geotechnical in the traditional way and the geoscience, and then we can slowly and steadily we can improve upon it. However, it is well established in the yes.
What I mean to say is we can do parallelly, simultaneously both the methods, and then compare.
I agree. Yes, yes. We can go parallelly. That is there. Because in the exploration of your mineral deposits, that is established. But in the geotechnical
It is
parameters,
yet to
it
be
is
established.
not yet
But
established.
the success story
You
of
have
tunnel,
given the yes, yes.
English Channel tunnel project indicates it is success.
Huh. Definitely. We have to go into details, and as I have told that this is a new topic for us. And
Yeah.
there is a new topic, we have to
So
search and analyze the things and then process it. It is a very wonderful. You
that,
have given the
that
example
is
of
why,
English
sir.
Channel also.
That
Yes,
is why, sir, I have requested the entire galaxy of experts to give a serious thought
yes,
to it.
yes. And further, you have given a very good idea that in the samples, we should take care of the distance between the samples and the elevation difference between the samples.
That is
So
the
then
basis
there
of
can
geostudies.
be accuracy. Yes.
That is the basis of geostudies.
And I can congratulate you for this wonderful lecture and thank you.
Thanks a lot. Thank you.
Thank you, Mr. Arora. I now request Dr. Dhawan to give concluding remarks for today's session.
Thank you very much, Mr. Mehrotra. Can you hear me?
Yes, sir. Yes, sir. I can very much hear you, sir. Thank you.
So it was certainly, as Mr. Arora has said, it was a wonderful lecture. And you have presented a very difficult subject in a very simple way and a lucid manner. Geostatistics is a proven technique for estimation of mineral reserve deposits or resource. And I think those who are working for mineral exploration and mining will certainly be benefited with today's lecture, because we shall be uploading it on YouTube also. Now, as far as geotechnical work is concerned, uh, certainly Mr. Mehrotra's efforts are worth appreciation. Certainly, we should give a very serious thought. But I will request Mr. Mehrotra to go into in detail. Particularly, he has given a very good example of the English Channel Tunnel. Now, what was actually done? How it worked for the selection of the final alignment? Because one thing which perhaps I could appreciate during his presentation today, that it established the zone in which marl was available. Although marl is also not a good rock, but certainly I think it was better than clay. So they could define the boundaries of the marl. But how it was done, whether it was applied on the drill hole data or because it is all undersea. So we should revisit the whole case and try to understand that how it was applied. So this is,
sir, if you permit me, I have
please.
a paper on this. Who had done this? I'll share with you.
Well, that is most welcome. But first of all, you will have to analyze yourself, and you should associate a good engineering geologist with you for this work, because once you say that it can be applied on the factors, the parameters uh, based on which the RMR is determined. You very rightly pointed out the 5 parameters which are used for calculation of RMR, and certainly it's a huge data. Many engineering geologists who measure many outcrops during their mapping, they will certainly be benefited. So first of all, I would take some cue from Mr. Arora also, wherein Mr. Arora said that it should be done side by side. You also said simultaneously. So maybe take up a project with a young geologist and see that how he is analyzing the data, and then apply your technique on that, and then let us and we can certainly have another open house in which, or a lecture from you, in which you should be in a position to tell that these are the results of the conventional analysis method or procedure, and this is how geostatistics is helping in the in analysis. So I think that sort of effort is required, and somebody will have to bell the cat. Prima facie, I think that this should be applicable, and geotechnical community should be taking it with a very positive mind. But I will just give you a word of caution that whenever somebody tries to do anything new, initially there is a resistance. So please keep on doing good job and continue to implement your thoughts. Maybe that initially people may not take it with a positive mind, but maybe once you prove it through one or two examples, everybody will run after it. Because something like this is very, very much required for analyzing geotechnical data of various kinds, not only RMR and Q values. There are so many, even it can be applied on the estimation of various sets of joints through, because today we do it with help of DIPS program, which is a rock science program. That is also a wonderful program. But maybe your method may give us a new light. So thank you very much for presenting your lecture at our platform DDAG. You are a part of us, and you are always very helpful.
I hope, sir, I did it within the time.
Oh yes, you have done it very well within time, and we are still having 3 minutes to go. So with these words, I conclude today's topic, and I thank everybody, including Mr. Arora and others, for joining today's lecture by Mr. Mehrotra. Thank you very much, Mehrotra sir, once again.
Thank you, sir. Thank you.
Thank you, Dr. Dhawan.
Sir, just I want to add one thing more, that I say that the topics chosen by the Mehrotra is very, very relevant and versatile. We have to take serious thinking on that, and we should go forward. And as Dr. Dhawan has suggested, that some more work has to be done, so that it is a new thing, and it in the geotechnical parameters, and it certainly we will benefit from that. Thank you, Mehrotra ji and Dhawan ji.
Sir, one thing I just wanted to add here. Let us take a live project.
Yes, yes.
A small part of a live project, and do it by both the methods, and then compare.
Yes, yes.
Okay. Yes. I agree. So let us give a big hand to Mehrotra ji. Thank you very much. God bless you.
Thank you, sir.
Thank you very much. Thank you.
I once again thank Dr. Dhawan, Mr. H.L. Arora, and the speaker of today's session, Mr. Mehrotra, for sparing their time and giving their sharing their views with us. So that's all for today. Thank you so much for joining. We'll see you again next month in the next edition of Open House by DDAG. Thank you.
Thank you.
Take care.
Thank you. Thank you. Very wonderful.